Hi, everybody. I hope you can see my presentation and presentation mode. Yes. Thank you very much, Mariano and Apostolis, for the introduction and talk opportunity. So today I'm going to talk about the Earth observation water quality products for different use cases produced for us in an operational manner in the frame of the PrimeWater project. So my name is Karin Schenk. I'm leading the water quality department of EOMAP. And of course, I'm presenting this on behalf of my colleagues. So my boss, Thomas Heege, but also my dear colleagues, Hendrik and Philip. Okay. So I will start with a short background about EOMAP and our methodology. So we are a spin-off since 2006 of the DLR, so the German Aerospace Center, and we are focused on mapping and monitoring aquatic environments. And this is the headquarters near Munich, where I'm sitting right now. So I'm waving. Actually, I would rather sit in Sardinia, but I sit now here. So we do worldwide mapping projects, for example, for drinking water, as presented here in this project, but also for hydropower applications, directive monitoring, environmental assessments, or climate change analysis. So here in these dark red dots, you see our worldwide projects. So they are basically spread all over. And yeah, to our background, so we use our own physics-based algorithms, which is called MIP and is orchestrated by the EWS. So that's our workflow system. And in this diagram, you see our workflow, which is consisting of taking the original satellite image report and convert it from the raw numbers to physical units, then land water differentiation, adjacency correction, suntane correction, all these very important steps to have a very robust product in the end. And we have then the water quality parameters and the quality control mechanisms included. As examples of water quality, what we can deliver are, for example, surface temperature, so it's the skin temperature, but also different water constituents like the turbidity or the related total suspended matter, color dissolved organic matter from fulvium and acids, or chlorophyll A, and also important, the harmful algae bloom indicator, which is an indicator on harmful algae blooms with sensitive to phycocyanin and phycoerythrin pigments. What we also have here included is our automatic quality control mechanism. So here you see an example of the already mentioned Melbourne water treatment plant. And in this case, we detect in the, let's say, winter time in the southern hemisphere a large solar zenith angle. So that's why this bluish color indicates a kind of a warning. There might be some errors in the product. So all these data are delivered to standardized interfaces and consumed by the PrimeWater platform, as Apostolis showed before. So I'm going to go to the data of the different use cases. So we have, as mentioned, the Lake Mulargia and Flumendosa reservoir. We have the Lake Heege and the Melbourne water treatment plant, the Lake Harsha. And that's what we have as count of records we used currently from 2015 to 2021. That's the time series we processed so far. So in total, for example, for Mulargia, we have over 360 single records, so measurements of data for these two reservoirs. For Lake Harsha, we have 210, Lake Heege over 260, and a little less for the Melbourne water treatment plant because it's a very small sized pond system where you can only use the Sentinel-2 with the 10-meter resolution. So we are focusing here on Landsat 8 and Sentinel-2 because the data is freely available from the raw level, and we can easily apply our algorithms. So that's the example of chlorophyll A maps from Sentinel-2 in April. On the left-hand side, on the right-hand side, we have Landsat 8 chlorophyll A concentrations of the two reservoirs. And you see that there's as Apostolis already said, that there's the clearer one in the northern part, so Flumendosa, and the more, let's say, algae bloom or turbidity influenced Lake Mulargia. So in case of any algae blooms or turbidity incidents, the Flumendosa reservoir is used to put in fresh water into the drinking water reservoir of Mulargia. So here we have a time series of the Secchitus test, also a very important parameter of the water quality. What we can see here are clear seasonal trends. So we have low values of Secchitus in wintertime with high turbidity, and low and high Secchitus, so good visibility in the summer months with the clear water conditions after bloom events. Another example, which I really like, is the water Melbourne Western water treatment plant. So here we see this system. We have on the left-hand side the chlorophyll A concentration of a Sentinel-2 image from 2021 in March. And on the other hand side, on the right-hand side, we have the harmful algae bloom indicator, which is indicating a quite diverse system, because we have in these very pinkish colors a high likelihood of harmful algae blooms, but whereas in the yellow and the greenish, we don't have a high indication of harmful algae blooms in this single image. So if you look at the time series, we don't see that much of a seasonal trend because it's a managed system. So that's why there are also short-term differences. I will show here some examples. So this is, for example, this image. And on the other hand, in a very short time scale, about 1 month later, we see total different behavior in the chlorophyll A values. So we have large differences in short time frame here. Another example is the legume, also in Australia, also a very large reservoir, and also prone to a lot of harmful algae blooms and algae blooms in general. And if we have a look at the time series of chlorophyll A, we see there's a huge difference also between the years. So we have 2016 with a lot of algae bloom events. And then we have the next year, 2017, with very low chlorophyll A values. I will have a look closer to now this example. So this is in April 2016. You see already that we have a greenish color in these RGB, and we have, if you see, it's very brownish, also the landscape, and the water level is very low. So the algae blooms typically occur when the water level is low. And then on the other hand side, we have the image from 2017 with high vegetation, or greenish vegetation around a higher water level and less chlorophyll A values detected. So we have here the large interannual variations. We also do in the frame of the PrimeWater project a lot of processor improvements, like the decoupling of chlorophyll and turbidity. So for example, in here, this is the example from the US, so Lake Harsha. They have high turbidity in wintertime, which is not typically or automatically connected to high chlorophyll values. But on the other side, if we have high chlorophyll A values, you have also a high turbidity because it's connected to the biomass. Yeah, so here you see these time series of Lake Harsha with the high values in the winter time of turbidity. So in 2016, always a little bit later than January, February. Okay, so this is already coming to my conclusions. So we can identify spatial and seasonal trends. We can support the local drinking water stakeholders by easy accessible information, for example, through the web platform. But still we have ongoing algorithm developments like the harmful algae bloom quantification, the finalization of the assimilation with modeling data, and also further validation exercises with in situ data. Yeah, that's already it. I want to thank everybody for their attention, and also especially to PrimeWater project, which we really like. Thank you very much.